This is another National Training Center Tech Byte. On liquid immersed transformer insulating fluids, we're going to be discussing Furan. You'll remember I referred to Furan in the first one that I did, associated with carbon monoxide and carbon dioxide found in transformer gas analysis. Tech Bytes are quick videos that will be from 3 to 8 minutes in duration to cover a very specific topic or issue associated with the world of electricity. This Tech Byte topic is associated with insulating fluid used in liquid-filled transformers, more specifically Furan testing. This training is derived primarily from IEEE Standards C57.152-2013 out of Annex E or ECHO. IEEE Guide for Diagnostic Field Testing of Fluid-Filled Power Transformers, Regulators, and Reactors. This training must be applied within the context of the IEEE standards and is meant entirely to act as a quick explanation of one or more specific gases and a refresher to the experienced engineer or technician. Paper is the major solid dielectric material within a transformer, used either as a conductor wraps and impregnated with insulating liquid, or as barrier boards, wraps, spacers, and clamps in compressed or resin-bonded forms. The major constituents of the paper are cellulose, about 90%, and lignin, about 6%, and the remainder is only about 4%. Each cellulose molecule consists of a linear glucose molecule polymer. These glucose molecules are held together through what is referred to as a glycosidic bond. A single cellulose fiber is formed from a number of these chains and held together by hydrogen bonds. Glycosidic means any of the numerous sugar derivatives that contain a non-sugar group bonded to an oxygen or nitrogen atom, and that on hydrolysis yield a sugar such as glucose. We depend on these structures in liquid-filled transformers to have good physical strength, and the degradation, as we discussed in the Tech Byte on CO and CO2, is a concern to us as we evaluate the condition and future reliability of our transformers. The three most common degradation factors of cellulose have been identified as thermal, oxidative, and hydrolytic. When cellulose is subjected to temperatures of 200 degrees C, the beta linkages or glycidic bonds tend to break and open the glucose molecule rings and thereby lose mechanical strength. The byproducts of this reaction include free glucose molecules, moisture, carbon monoxide or CO, carbon dioxide, CO2, and organic acids. The presence of oxygen promotes oxidation, and cellulose molecules are prone to oxidize. The reaction of oxidation on these cellulose molecules causes what's called the glycosidic bond to weaken and can cause scission, which is the breaking of the chemical bond of the cellulose molecule chain. With water and acids present, the glycosidic bond is exposed to slicing that in turn produces free glucose. Hydrolytic degradation can be initiated out of thermal and oxidative degradation, since both of these degradations produce moisture and acids. From our carbon monoxide and carbon dioxide Tech Byte and our discussions here, it can be observed that the immediate byproducts related to paper degradation are carbon monoxide or CO, carbon dioxide, CO2, moisture, organic acids, and free glucose molecules. The free glucose degrades further into aromatic components known as furans. The presence of moisture and organic acids in the insulating liquid can further degrade the free glucose molecule into what we call 5-hydroxymethyl 2-furfuryl, which is 5H2F. 5H2F is an unstable compound and can decompose further into other furans. These other 4 furans, for a total of 5, are 2-foraldehyde, 2-FAL, 5-methyl 2-foraldehyde, 5M2F, are 2-acetylfuran, 2-ACF, and finally, for furyl alcohol, 2-FOL. All 5 compounds previously mentioned are known as furan derivatives. It's been shown that all of these compounds, except 2-FAL shown here, are not very stable under operating conditions found in transformers. These compounds apparently form and then further degrade to the 2-FAL molecules shown here over a time span of a few months. 2-FAL is apparently stable for several years under the same conditions. The method of sampling should comply with ASTM D923 to ensure sampling integrity. If you've already been sampling transformers, this is the same method you're already using. Once the furanic compounds have been extracted, the furan concentration is then measured in a laboratory using high-performance liquid chromatography, HPLC, and an ultraviolet detector. The technique for testing is described in ASTM D5837. There are multiple papers that discuss the value and interpretation of furan data, but there remains no exact guidance for interpreting the results. The concentration of furanic compounds gives an indication of the condition of the paper in terms of degree of polymerization. While the rate of change of furan concentration can indicate the rate of aging of paper, generally the total concentrations are less than 0.5 ppm, and in some cases these levels may be maintained throughout the transformer life. The types and concentrations of furans in the insulating liquid sample can also indicate the occurrence of abnormal stresses in a transformer, whether short duration overheating of the insulation or prolonged general overheating. That statement is directly from IEEE C57.152-2013 Annex E. And other than a few recommendations which we're about to cover, that's all that standard will really tell you about furan or furan evaluation. In conclusion, furan testing must always be used in conjunction with other data. IEEE recommends furan testing after a protection trip due to internal fault. IEEE leaves it optional for commissioning, in service, and after an external fault. The optional testing is best used as part of a condition-based program. Ideally, we would like to see the furan run on any transformer of significant size and or criticality upon commissioning to use as a baseline for future trending. It is generally accepted that any furan component of less than 10 ppm is acceptable. For higher levels, the estimated degree of polymerization is evaluated by the labs. New insulation with a high degree of mechanical strength will typically have a degree of polymerization of 1,000 to 1,300. Middle-aged paper is approximately 500, and paper with less than 250 is in its old age. Severely degraded insulation with a degree of polymerization of 150 or less will have very little mechanical strength and may result in a transformer failure. The above estimations are based on a study by Chin Dong of GSU transformers filled with mineral oil. This science is continuing to evolve, and more papers are being written and more research is conducted. Do not confuse the furan component in ppm with the estimated degree of polymerization. In conclusion, if you have carbon monoxide and carbon dioxide that are concerning and have not ordered a furan test, it might be a good idea to do so. This ends our Tech Byte on liquid immersed transformer insulating fluid and concludes our discussion of furan.